Welcome to the deep dive. We take those highly technical papers you share, and, well, we dig in to pull out the insights you need right now. Today, it's all about structural safety, specifically how engineers try to model and prevent something called progressive collapse.
Yes, it's probably the failure mechanism engineers fear most. Progressive collapse, essentially, is when a small local failure, maybe one column gets damaged, doesn't just stay local.
It spreads.
Exactly. The damage propagates element by element, and you end up with this disproportionately large failure, potentially the whole structure.
And we've seen this happen tragically. You don't have to look far back. The partial collapse of Champlain Tower South in Florida back in 2021. Failure of D-beams was part of that story.
Yeah, key factor, yes.
Or, the Genoa Highway Viaduct failure in Italy in 2018. Started with a single-stay cable rupture. Even fires, like the Wilton Pace de Almeida building in São Paulo. Fire weakened key parts, leading to a collapse that was, again, way out of proportion to the initial damage.
The trigger can vary. Impact, blast, fire, degradation. But the core issue is the structure's inability to find a new way to carry the load once an element is lost. That's what makes it progressive.
Right. So our mission today is to really get under the hood of the simulations engineers use to predict these terrible events. The sources you sent us compare the two main numerical methods for modeling reinforced concrete frames.
That's right. We're looking at the displacement-based, or DB, formulation versus the force-based FB formulation, and specifically how they stack up in these nonlinear quasi-static pushdown tests.
Okay, pushdown test. For anyone listening, what does that actually simulate?
It's the standard way we model this.
Yeah.
You basically digitally remove a critical column, like one supporting several floors.
Okay.
Then you slowly apply vertical displacement downwards, pushing on the structure above the removed column to see how much load it can take before it, well, completely fails.
And to do that accurately, you mentioned these advanced tools, distributed fiber sections. Why are those needed?
Good question. They're essential because, you see, concrete and steel behave very differently under extreme stress. Concrete cracks, steel yields, maybe the rebar even fractures.
Right.
Fiber sections let us model the concrete and each individual steel reinforcing bar separately within a tiny cross-section of a beam or column. It gives us that really granular view of damage needed for capturing this extreme nonlinearity.
Got it. So within that detailed fiber modeling, we have these two competing approaches, DB and FB. Let's start with the displacement-based.
Okay, displacement-based, DB, it's often called the stiffness method. It's probably the more common one you'll find in standard software packages.
What's that?
Well, it works by assuming a shape, approximate displacement field, along the element to figure out the deformations. It's generally quite efficient computationally.
But there's a catch.
The catch is its accuracy really hinges on those assumptions, and specifically how finely you chop up the structure into elements, your mesh refinement.
Okay, and the alternative, force-based FB.
Right, the flexibility method. It's maybe less common for this specific type of analysis in some circles, but it has a significant mathematical advantage.
Which is?
It guarantees, mathematically, an exact equilibrium between the forces acting on the whole element and the internal forces within its cross-sections, even when things get highly nonlinear.
Exact equilibrium. That sounds pretty important when you're modeling collapse.
It is. That precision in balancing forces is its key strength.
Now, the study found that initially, when everything's still behaving nicely in the linear range.
Yes. In the linear elastic part of the pushdown curve, both DB and FB give pretty much the same answer. They agree on the structure's initial stiffness.
But then the pressure mounts, things start to bend and crack, and you hit the nonlinear zone. What happens then?
That's where they diverge. The study consistently showed that once you get into that highly nonlinear range, the displacement-based models predicted higher resistance.
Wait, so the more common DB method suggested the structure was stronger in the failure zone than the FB method did.
Yes, exactly. Holding everything else constant, the DB simulation showed the frame could withstand more downward push before failing.
Why would it do that? Why is it sort of artificially optimistic?
It goes back to those assumed displacement shapes. When you get very localized damage, like a plastic hinge forming, the simple shapes assumed by DB might not capture the very steep changes in strain accurately. This can effectively make the element seem stiffer than it really is right at the point where it should be softening dramatically and failing. Which brings us back into the main challenge here, modeling that damage zone, that plasticity, correctly.
Right, the zones of concentrated plasticity. This sounds like where the real modeling headaches begin. For the DB approach, if it tends to overestimate strength, how do engineers counteract that?
Basically through brute force meshing. For DB models, you have to use a much finer, mesh more smaller finite elements, especially in those critical zones, like the ends of beams where hinges form.
Well, especially there.
Because if you use a large element spanning that critical zone, the model averages out the behavior and just won't capture the intense yielding of the steel rebar accurately. You need small elements to see that localized failure.
So think of a beam as Lego blocks. DB needs really tiny blocks where you expect the damage. What about inside those blocks, integration points?
Interestingly, DB isn't very sensitive to the number of integration points within each element. It's mostly about the size of the element itself.
Okay, so DB cares about element size, not so much internal sampling points. What about FB? Does it have the same sensitivity?
No, it's quite different. FB flips the script. Its accuracy is highly sensitive to the balance between the element size and the number of internal integration points used to sample the stress and strain.
A balance. How so?
If you use fewer, larger elements with FB, you generally need more integration points inside each one to capture the nonlinear behavior accurately.
So could you just max out the integration points to be safe?
You'd think so, but no. There's a problem if you use too many. The sources point this out clearly.
Yeah.
It can lead to a non-physical issue called strain localization.
Strain localization, that sounds bad.
It is. Imagine the damage, the yielding, should spread out realistically over a small region. Instead, strain localization forces all that inelastic deformation to concentrate artificially at a single point, like a numerical crack forming instantly.
So it's not physically realistic.
Not at all. It leads to the model predicting a sudden, premature drop in resistance, and it can completely mess up the simulation's ability to even converge to a solution.
Okay, so for DB, it's get the mesh fine enough. For FB, it's find the right balance between mesh size and integration points. Not too few, not too many.
That's the core challenge. And case study 2 in the research really highlights this trade-off.
Yeah.
They modeled a full-scale bare frame.
A frame with just beams and columns, no walls.
Exactly. And they compared the simulations to actual experimental results to get good agreement with the experiment. The force-based model only needed 2 finite elements at the critical beam ends, where the plastic hinges were expected.
Okay, 2 elements for FB and DB.
The displacement-based model needed 4 elements in those same zones to achieve similar accuracy.
Wow. Double the elements for DB in the critical zones?
Roughly double, yes.
Yeah.
And think about scaling that up. If you're modeling a large building needing twice the elements in potentially many critical regions, that's a huge increase in computational cost. More processing time, more memory.
A very practical consideration for engineering offices choosing their tools.
Absolutely. DB might seem simpler conceptually, but that mesh requirement can be a major hurdle for large, complex collapse simulations.
Okay, so we've established the baseline for a bare frame, columns, and beams only. Plasticity happens where you'd expect, mostly at the beam ends near the columns. Standard stuff.
Pretty much textbook, yes.
But now, here's where it gets really interesting, according to the research. This is where the conventional thinking gets a major shakeup.
You're talking about the masonry infill walls.
Exactly, those brick or block walls that fill the spaces within the concrete frame, often treated as just, partitions or non-structural weight.
But they're not passive. The study modeled them properly using a common approach called a macro 3-strut model, which captures their ability to resist forces.
And what did adding these walls do to the way the frame failed?
It fundamentally changed everything. The infill walls completely redistributed the nonlinearity, the damage.
How so?
Instead of plasticity concentrating only at the beam ends, the presence of the walls forced plastic hinges to form not just at the ends, but also in the middle region, the midspan, of the beams next to where the column was removed.
So the damage wasn't localized anymore, it spread along the beam.
It spread out significantly. The wall interacts with the beam, changing the internal forces completely.
That sounds like it would make the structure behave very differently. What did it do to its actual strength? Let's look at case study 1, the 1/3 scale model.
The numbers are striking. At a small vertical displacement, just 12.7 millimeters, barely half an inch, the bare frame, the one without walls, was already struggling. It could only resist 23.50 kilonewtons.
23.5, got it. And the frame with the infill walls.
At that exact same 12.7 millimeter displacement, the infill frame resisted 146.37 kilonewtons.
Whoa. Okay, wait. 23.5 versus 146.
It's an increase by a factor of 6.23.
6.23 times stronger, just because of the infill wall in that early stage.
Yes, it's a massive difference. It shows the wall isn't just dead weight, it's acting as a primary load-resisting element, especially early on.
How does it do that? What's the mechanism?
It works through what's called compressive arch action, or CAA. The wall forms a kind of diagonal compression strut, pushing against the corners of the frame, carrying a lot of that initial vertical load.
Like an arch supporting the load.
Exactly. The masonry wall acts as the first line of defense. It takes a hit. It only starts to lose its load-bearing capacity after the structure goes past its peak resistance.
And by then, hopefully, the frame itself has engaged other mechanisms, like catenary action.
Right. After CAA diminishes, the goal is for the frame to transition into tensile catenary action, TCA. That's where the beams, particularly the steel reinforcement, start acting like, well, like a hanging cable or chain, using tension to bridge the gap.
Sort of a last resort mechanism.
A very important one for large displacements, yes. And the infill walls help here too.
How?
They significantly delay the point at which the structure has to rely solely on that catenary action. In the bare frame study, the transition from CAA dominance to TCA dominance happened at about 210 millimeters of vertical displacement.
Okay. And with the infill walls?
That transition point was pushed out to 242 millimeters. The walls help the structure maintain its integrity and stiffness for longer, delaying that final, more flexible catenary phase.
So the walls provide huge initial strength and improve resilience later on. This really changes the picture. How does this affect the choice between DB and FB modeling we discussed earlier?
Well, because the infill walls spread the plasticity out, it's not just at the beam ends anymore, it's also happening at the midspan. You can no longer just focus your fine mesh only at the ends.
Oh, right. The critical zone just got a lot bigger.
Exactly. The entire beam adjacent to the removed column potentially sees significant nonlinearity. So if you're using DB,
You need that fine mesh along a much greater length of the beam, not just at the very ends.
correct. And if you're using FB,
You need to carefully manage that balance of elements and integration points over a wider area too, being wary of strain localization anywhere along that beam.
precisely. Modeling an infill frame accurately requires a more detailed discretization strategy overall, regardless of the formulation you choose, compared to a simpler bare frame.
And this isn't just academic, right? You mentioned engineers are actually required to do these kinds of analyses.
Yes, design standards and guidelines like those from the GSA and DoD in the U.S. often recommend or even mandate these types of nonlinear pushdown analyses for assessing progressive collapse risk, especially for important buildings.
So understanding these modeling nuances, DB versus FB sensitivity, the huge impact of infills isn't just about getting the theory right. It's about whether your safety assessment is actually reliable.
It's absolutely critical. Getting the modeling wrong because you didn't understand these sensitivities could lead to a non-conservative prediction thinking a structure is safer than it is, or it could lead to a non-physical result that just doesn't reflect reality. Neither is acceptable.
Okay, so wrapping up the main takeaways here. Your choice of modeling method, DB or FB, dictates where you need to focus your meshing effort and sensitivity checks. DB needs fine mesh and plastic zones. FB needs careful balancing of elements and integration points.
And the second big point, never underestimate the humble masonry infill wall. It's not secondary. It fundamentally changes where and how the structure yields and can boost initial resistance by, well, a factor of over 6 in the cases studied.
That's a powerful insight. The research you shared was based on these detailed numerical models, carefully checked against experiments, but the authors themselves mentioned the next step, right?
Yes. The big frontier is incorporating uncertainty. Real-world materials aren't perfectly uniform. Rebar strength varies slightly. Concrete quality varies. The way the masonry is built varies.
Which leads to a really interesting, maybe slightly unsettling final thought for you, the listener. If things we can't perfectly control, like the exact strength of the mortar in that infill wall, or slight variations in steel properties can significantly influence the collapse behavior, then how much faith can we place in any single simulation result? How truly reliable is a deterministic analysis when faced with the inherent randomness of the real world? And what's the maximum safety we can realistically engineer against these complex, potentially catastrophic events?
It pushes us towards thinking probabilistically, not just one simulation, but thousands, exploring the range of possibilities. It's about understanding the risk profile, not just a single number. That's where the field needs to keep moving to really enhance structural safety against these extreme events.
Definitely something to think about. Thanks for joining us for this deep dive.